Well, I'm really, really glad to be here. Frankly, this is going to be part history and part discussion. I would like all discussion, but I'm going to kind of seed the discussion. I had Morse calculus in 52, 53. You got that right. It's 1952 and 53, not earlier. First, I want to raise a question. I'll first make kind of an assertion. In my view, there's three goals for a calculus course. One is, I'll roughly say, cultural, that at a nice university, that the introductory course can be not necessarily a watered-down one, but one that turns you into a semi-practitioner for life. My geology course at UT was like that. I just say something against geologists. Well, that's a personal attack for me, even though I had no intention of ever doing geology. Drive through West Texas and see the road cuts. Why, I have a good time with that. The next is it's absolutely an imperative. You want to prepare people prepared for the courses that use calculus. You need to know what that is. You need to prepare that. You don't want to sacrifice that for anything. And third, you want to search for mathematicians. Now, a first question, maybe I won't ask for answers right now, but I want you to think about it. To what extent do these need to have separate courses for these constituencies? There are three quite different goals, and one might think they're in conflict. You can both formulate your own answer, and you can guess what mine is, and I'll review that. I already explained the cultural and the preparation for engineering and physics courses and such are sort of self-explanatory. But I will add that there doesn't need to be any particular compromise on things like notation for that. And I'll digress a moment about the present plague of standardized testing. Teachers can be put in fear of having their students not doing good enough. My own contention is that if they teach a really good course, that can be included. The late Bill Behavior taught with him for many years at several institutions. When there was a discussion of a curriculum or change in the courses, he was an absolute genius. He would get a hold of the engineers that were in charge of this issue, or the physicists, and he would get the drop on them. He'd say, "What do you want them to know?" He'd never get to a table of contents and let them say this chapter, that chapter, because they're hopeless about piling it on and wanting people to be a mature practitioner when they're just not. Well, so they'd tell him the half a dozen things of their priorities. Okay, we'll promise it, and then he delivered it. But he did it in kind of the spare time of the course. He taught the course he wanted, but just in the spare time, he covered these things. He just made sure they did. Boy, just a genius. Boy, if he ever got into table of contents, well, he'd be just hosed. So with the standardized testing, my feeling is that if your students, if you really wake up their brains and they really start becoming much more of a practicing intellectual, that you could prepare them, provided you know what the standardized test is like, you've looked at them and you know what's there. I'm not saying give them the answers, but if you know what's there, that you can cover that stuff in your spare time, and you have nothing to fear. Now, of course, you have little to fear. Of course, if you're teaching a course and you want nothing to fear, then you're in trouble. Now, my model for teaching, and Gordon's and a bunch of others, is the Nuremberg war crime trials. What came out of that? What lesson for humanity, just in short? That you follow your conscience and not orders, ever. That's what it says. You follow the orders, you pay for it. You follow your conscience, no matter what happens to you, you're ahead. And with the teaching, if you're not supposed to do it, and you feel that, you hear your life is intersecting the life of these students for a semester or so, you have this tremendous opportunity. And if you don't grasp it out of some fear, then you've lost it. But you don't really have much to fear. And if somehow they suffered because you didn't turn on the fire hose and stuff it down their throat, that they came out a human being with diminished prospects, well, that's tough. You did your best. So I believe those things can be taken care of. Now, Joe Iles wrote a dissertation in the School of Education at UT. He had a lot of mathematics. And at my instigation, if you can imagine my doing something like this, I said, look at the grades and such of at UT where there was applied and pure. The applied was the physicist's little brother as far as attitude on life is concerned. And the pure, we kind of have a grasp of. Well, if you look at the grades, we blew them out of the water. The notation was different, the attitude was different, but the pure mathematics students, almost to the person, learned how to use their minds, were beginning to use their minds as a surgical instrument. And it was just a Cro-Magnons versus Neanderthals. I'm not sure which was on top, but they're quite different. And there was no contest. Well, people can use their brain, there's just nothing to fear. Now, another thing with calculus, a very pet thing, is the notation that's used. I'll come out right away. The old guys in the late 1700s and 1800s, they were doing, by and large, the best they could with their ghosts of departed quantities. But they're basically an atrocity. Now, if anybody wants to take up the time here to define dx for me, I'll listen, but you'll have a fight. But maybe you'll win, but I doubt it. The notation is terrible. Now, I've had a parallel life in consulting since the 50s. And frankly, I've made a small fortune out of correcting the troubles that all that stuff brought. I've seen months and months wasted, especially on partial derivatives. You get a bunch together in a dorm room talking about stuff and maybe consuming some stuff, and the question comes out, what's the difference between a partial derivative and a total derivative? Oh man, they don't know. They don't know. That costs the economy billions a year, billions, maybe trillions, because people don't know that. The notation is terrible. It's just got to go. Now, if you can give me a definition of differential, you should get it to me one way or another, not today, some other way, but you can't. It's never been defined to cover the uses in calculus. And the stress that induces, the negative things that induces from trying to use something that can't, sometimes you want to use things that haven't been defined, but you never want to use things that can't be defined, and in particular that you can't. And these differentials, you can't, you just can't. You can apologize, you can say it's cleared up in differential geometry. No, it's not. No, they use them in a consistent way, but it's not cleared up. They don't use them in a way that covers all of the half a dozen plus ways that calculus uses them. An antiderivative problem you just morph into from one use to the other without saying anything. And then the rule of the game is you never question that. So that's got to go one way or the other. Now, I have some notes posted there. If you can remember, legacy, that's what we're at right now. And legacy, R.L. Moore, all one word, no dots. You can remember legacy, rlmoore.org, and then put a slash, and then have calculus, and up it comes. It's maybe a third of Moore's calculus class, but actually the version that got posted had students' names by them. They get up and present the problem, and then they'd sign my sheet, and that was theirs after that. Now, a good bit of Moore's success came from he just completely rethought it. No DXs, no DYs, ever, except, sometimes he could put on, literally, or figuratively put on his straw hat and his cane and do a little pantomime or something about how people use that. But I never mentioned it except in jest and derision. They would never think it was serious that I'm giving the other side. I mean, I'm not giving the other side that's equal with mine. I'm not. I don't present it that way. Well, so I asked, do you need separate courses? Well, I'll go on a little I'll describe Moore's course. The minute he walked in the room, you knew there was something special. It was just something special. And I'll tip my hand. He had it figured out how to integrate these three things. It met 3 times a week, but we had time for everything. Discussion about everything, things from the newspaper, the student newspaper. It was a cultural thing. And he definitely did the preparation for the other courses. We probably were as good at finding antiderivatives as humans ever get. We just were absolute tigers with that. Just couldn't be bested on it. Never with a curly S or a D or anything. We did the trigonometric substitutions, and every statement was right. There wasn't a proof there because we didn't do proofs yet. The proofs were next year. Except there was kind of a subrosive thing where he was infecting people with a limit idea. Well, in our class, 2 people caught on. Neither was me. It was Worrell and Appling. Worrell's well known to this group. Appling came just once, and that's too bad. But they caught on. They had a reasonable education. I had a terrible education by classical standards. But boy, I was left alone, and that was worth all the tea in China. But anyway, he clearly, in retrospect, he clearly had that in mind. And he would feed us a little bit, but we knew it wasn't, nobody would dream of asking, is this going to be on the final? He gave the definition of continuity about in February as a full year course. Okay, the alpha, beta, H, and K. Nothing. Boy, it was just poetry to a dog. I just didn't get anything out of it. Summer, I took a bunch of physics course, actually dropping his geometry course to concentrate on physics. He got a little moisture under there. He said, don't let this deter you from taking more mathematics. Well, it didn't. It took a couple of years before I got back with him. But anyway, he gave it in about February. Well, I didn't think so much about mathematics in the summer. Took Wall's differential equations in the fall, September. First thing, well, at the end of the first class, he asked us to give a definition of continuity. Classic Texas style. You raise the interesting things when there's no time for discussion. And let you stew on that. Well, then to my astonishment, the next class, he asked papers to be handed in. He almost never had anything ever handed in. Well, so he got some. He pointed out, not right, and such. He wanted to know where the class was with this. He got to mine. Boy, it was dirty and probably blood on it and written this way and that way and every way, but he just kept turning it and following it. It wasn't made for human consumption other than mine. After about 5 minutes of looking at it, he says, that's right. And so it was just writing that thing out. That's where I'd learned it, in writing that thing out. Okay, well, that's a long time. If you're lecturing and you come up with continuity, can you tolerate 6 months? Well, I was tolerated 6 months. Did I learn continuity? You bet. World class. I'd take my knowledge and feeling for continuity and stack it up anywhere. I'd really learned it. but it took 6 months. Well, now in the context of something that took humanity, the best brains of humanity, 2,000 years, and me with a nice little boost, but just a little boost, takes 6 months. That's not so bad. 6 months to 2,000 years, that's a speed of light practically. But that's how long it took me. Now, did he put me out on the street because I couldn't get it? No. He knew, he really studied, another big point, he studied his students. He really studied them. Bill Mahaver was a past master at studying his study of students and how he treated various people, just like they needed to be treated. If they needed to be taken down a little bit, he'd do that. If they were kind of insecure, they'd do another thing. If there was a budding intellectual that hadn't fleshed things out for themselves, like me, he kind of let us alone. He didn't pound us or anything. He let us alone. But now, my particular class had got 3 research mathematicians out of it. That was kind of a mediocre year. He'd try for more than that. One little quote I have to give. He said, should everybody be a mathematician? No, he said, but they should all want to be. And that's the way it is with these courses. You take a course, a really good course, and you kind of want to be that. But, well, okay, so I gave some background. I just wrote this out a few minutes ago. But now this stuff I suggested you could download, it's not a teacher's manual. It just gives the name, rank, and serial number with no explanation at all. But he gave us these all the standard derivative problems. And then people got up the board and made their mistakes or not, or got through it. A few years ago, I gave that Harvard, they wanted me to, it was an impossible thing, but they wanted me to give the example of the first day of calculus the way I taught it. So mine's the same way that Moore does. Well, so I got they were selected people, juniors and seniors, and I got them up to the board. Some of them probably for the first time, I got them up to the board. Guess what? We sort of worked through p squared minus a squared over p minus a with a little help from me and a little help from them. Then I posed the f of x is x cubed for all x. What's f prime? And we started out p cubed minus a cubed over p minus a. They made the same mistakes that the North Texas did. They used the binomial theorem to factor p cubed minus a cubed. That was just Harvard. It was all a select group of juniors, mathematics majors. It's a wonderful place, but I mean, they don't have a corner on stuff. Well, so that's kind of it. And I'm willing to turn it over to you about the question, the three aspects of calculus. Do they need to be the same? Like Stanford has 3 levels of calculus. The certified genius applies. One more story about that. A brilliant fellow that I consult with out in California. He's a member of the Research Institute. I work with him. He's totally positive. He went to the University of Hawaii for his bachelor's degree. He went to Stanford and worked with great distinction with Percy Diaconis, one of the best probabilists around. I said, did you teach when you were there? Yeah, I taught. What'd you teach? Calculus. I said, oh, I bet they're really good. The only negative I heard him say in years of association with him, he says, no, he says, what they're good at is filling in the bubbles of standardized tests. Oh man, it's sad. They were totally burned out from what they had to do to get in there. Now I probably stepped on some toes here, but that's okay. Well, anyway, they had it split into 3 with decidedly mixed result. Well, what do you think? Who wants to say? Should we split it into 2 or 3? Do we have to maximize the progress of the various constituents to sort of mold it to where those students are, or we just throw them in together?
Robert Mendez, University of Houston.
University where?
University of Houston.
Okay.
I like to believe that you should put them all in the same room. I think that you described a differentiation scenario where you have, you knock down those that need to be knocked down, and you raise up those that needs to be raised up, and you leave the ones alone that can be left alone, and you should be able to handle, excuse me, you should be able to handle all of them.
Okay. Anybody else? What?
Ed Parker, retired from James Madison University and more recently Guilford College. The calculus is even more difficult to teach now than it was in the 80s because so many students have already had it. But I agree with the thing over there. Is the problem is finding a way to take the things that you pointed out as being the problem and trying to turn them into a positive. The key for me has been to make the first step, regardless of what the mathematics was, for them to articulate it within the language I've given them to work with. And it doesn't succeed globally, but the ones that do succeed at that always succeed with the mathematics. So there's a marker there. I don't know how to make it happen globally, but when it does happen, then the students always succeed.
Let's give this guy a chance.
Thank you. Stephen Jones. I guess because of my talk yesterday, I've got to take the position that the reality is that while Moore wouldn't use dx dy, you're going to use that.
I'll say again.
Moore never used the derivative sign. He
Right.
had a function for it,
Right.
and so forth. But unfortunately, when you get up to your physics and your engineering classes, they use it. And that's a reality. Whether it really means anything or not, they use it. And I think in my talk yesterday, I said I had real difficulty because every time I saw that, I had to mentally translate, what does this mean? And that took just too many extra steps, and I just never caught on to the mathematics that they were using in upper level physics
caught on
classes. To the mathematics as they used it in upper level physics courses. And I kind of think that, yeah, unfortunately, the reality is I would separate those. I would separate those that need to understand the foundations of calculus, the math majors, and those people that are using the calculus as a tool, as a language to use in other classes. So I would separate the classes.
I'll add that people can really jump the stereotype that one might attribute to them, and they can get out of that class. Of my 30 PhD students, about half of them started out in engineering or physics, and they probably had no intention of being hooked, but the hook they got. David?
Well, I was going to say, if you have these three goals and you want to divide the group into three classes based on those three goals, and one of them is to find mathematicians, I would be hard-pressed to know which ones to put in that group.
Which ones?
I would be hard-pressed to know which ones to put in the group where you're looking for mathematicians, because they might be anywhere.
Paul Forrester, Alamo Heights High School, San Antonio. At the high school level, we do not have the luxury of separating them into this one, and that one, although we do have A, B, and BC calculus.
That's good.
Which are supposed to be the same thing, but at a different pace. So in high school, our objective is to make the course a multilingual course, to make them understand that dy dx, f prime of x, y prime, d dx of y, d dx of f of x, and d sub x of y all mean the same thing. They're just different symbols for the same thing.
They kind of mean the same thing, but
anyway.
but the dx has no counterpart in the real world.
You can say that the dx has no counterpart in the real world. That's just a symbol they use, if you wish. But we need to make them literate, because we don't know where they're going to wind up and what field they're going to wind up.
You can tell them how the most of the rest of the world speaks and communicates. You can just tell them that. Preferably with a straw hat and a cane and a little music that you just kind of go out sideways on the stage.
We need to teach them their different ways of expressing the same thing.
Yeah, it just comes at a certain time. I found that as the years went on, first students had no calculus, and now almost all of them have some. some pretty tough individuals come up with near tears in their eyes. Why couldn't they have told us what was going on in high school? Why couldn't they have told us? No, big fella, just you'll see. You're just seeing how life is kind of tough, and that's what you're getting. That they're the big scam perpetrated on you, and get used to it because there's going to be more.
Quick question.
What?
Quick question. Did more...
Closer to the microphone. Speak up.
Did more discuss applications?
Oh, yes. Oh, yeah, I'm glad you answered that. We worked one good, solid problem of kind of every kind that calculus would have, given of some kind of weird-looking three-dimensional figure, given the density at each point, what's the mass? Well, we worked it out. And we used a scheme that in retrospect was crucial to proving the fundamental theorem of calculus. Just having squeezing and inequalities. We didn't just finish with the epsilon delta thing, but that was the only thing we lacked. But he went way beyond usual applications. He said, we have water behind a dam. What are we assuming about that? About the pressure that it goes, that it's more at the bottom than at the top, and so on. And he did physical axioms for that. That's way beyond the usual applications. And in my research papers and such, I've had difficult and crucial multiple integrals. And I just think about my calculus class and it bails me out. It's the only way I can do it. The cowboy tactics aren't any good. I've got to really know about that. And I go back to putting the squeeze on things and I get the right answer. But he was a big applications guy. But he managed to do this all in one group. Let's say you never know what group somebody's supposed to be in eventually. And they make these leaps. They think they one thing, but they found what they want to do with their life, a good bit of it. You have them sort of segregated to their own kind. Well, you've denied them a lot. And some of them think they're good at mathematics and want to do it, and they don't have the stomach for it. They need to find it out too. And they need to find out that memorizing a bunch of stuff like they learned in their prep school is not a particularly great strategy. Am I running out of time? You're standing up.
Almost. I think we have time for maybe one more question.
Okay. Anybody just make a general comment like you're all wet or something? This is a short thing. If you download the problems, it's just pure Moore's calculus most of the way. But when you get to logarithms, it's stuff I got from Wall that's well documented in his creative mathematics, and that kind of follows through. But it gives you a taste, and it could say a lot more about how nicely that the antiderivatives can be done with every statement. If you wrote the best paper of your life and you wanted it really good and you needed an antiderivative, well, you could use what we learned there. You put a bunch of dx's in there and you don't know. Now there's one thought that I had that I was, yes, I think important admonishment here. I've never been shy about working it in, about how much I work on mathematics, how much I work on it. I want them to know that, and more certainly wanted them to know what he'd done in life was well enough known that he didn't say much about it. But I want them to know that what I'm trying to do is invite them to this group of people that spend a lot of their life looking, not out of charity, but just because they want to know. Out of charity is not a good motivation. That's not good enough. You have to just want to know. But let them know your involvement in mathematics. Written some research papers, just let them know you did that. Moore gave a lot of practical experience on that. He said one time he wanted to write a paper where every, that was just like a legal document, and he didn't shoot the breeze at all to put it in a human setting. He really worked hard on it, and when he worked hard, it was formidable. What happened? The paper came out, he went to the library, he looked at it. First page, a big gaffe. It just cured him from taking the humanity out of his arguments. He wanted enough stuff there that if there is a mistake, that you can figure it out again. He also said one final thing. Somebody was praising somebody's clear thinking. He said he didn't think that was a high priority, clear thinking, even critical thinking. You just wanted this drive to get something, and you'd eventually think critically about it. If you wanted to know enough, you'd think critically. So he didn't disparage clear thinking, but he didn't think that was way down the list. Now I'm out of time, right?
You are out of time.
Am I way over?
Not way over, but let's thank our speaker.
Thanks.